Hello. So as we saw in the previous video, the idea behind valence bond theory is that we're going to think of the atomic orbitals in individual atoms overlapping to form bonds. And so we're going to start here talking about the first possibility for hybrid orbitals, where we have our s and p orbitals combining on a central atom to form sp3 hybrid orbitals. So again, these orbitals are going to form a tetrahedral geometry. So if we have something, say, like as we looked at in the last video, something like methane, where we have carbon, we're going to have orbitals that point along the same dimensions as we have for our tetrahedral structure. And then some other molecule can come along with its atomic orbitals and overlap. And we saw that with hydrogen 1s orbitals will overlap, and these form our bonds. All right, and these, again, these types of bonds where the electrons are found in between the atoms are what we call sigma bonds. So we can say that the orbital is along the internuclear axis. Now that's a really fancy word just to say that it's pointed right. That is the line that goes right in between the two atoms. So just saying that if you draw a line directly from carbon to oxygen, let me use a different color, that is the internuclear axis, and that's right where the electrons in the bond are found. So the highest probability is there. Okay, well, this is what it looks like if we have four bonds. What about if we have lone pairs? Well, we can view lone pairs as, just like we do when thinking about other geometries, we can think about the lone pairs as occupying one of these spots in these hybrid orbitals. So we can look at, say, something like water, which we've looked at this structure before. So, right, the Lewis structure for water, we've seen many times, looks like this. And so anything that forms a tetrahedral geometry is going to have sp3 hybrid orbitals. Because that's what those orbitals are. The sp3 hybrid orbitals are the orbitals that make a tetrahedral geometry. That means the electrons are arranged in such a way that we get our four directions that point along the tetrahedron. So if we want to draw what's going on here, again, we're going to have our sp3 hybrid orbitals. And I'm going to draw the wedge and the dashed line to indicate that these orbitals are pointed along the tetrahedron. All right, and so these are where our electrons are. But two of these are occupied by lone pairs, and so we'll represent that by putting two dots in it. Whereas here we're going to have a bond. These are our hydrogen atoms here and here, the 1s orbitals on the hydrogen atoms. All right, so we still have our sigma bond forming in each of these spots here, where the 1s orbital on the hydrogens overlap with the sp3 hybrid orbitals on the oxygen. So we still get the same overall structure, the same overall shape to the molecule, the fact that we have this about 109.5 degrees, a little bit less than that. All of that is the same as what we learned about with VSEPR theory. But now we're just understanding what's happening with the electrons and where are they at specifically in the molecule. So we could do this with any number of lone pairs as well. So if we had, say, only one lone pair, we'd still get a trigonal pyramidal structure, still an sp3 hybrid orbitals, and we'd get the overlap in the bonds, and the lone pair would be just by itself in one of these orbitals. All right, so that's the basic idea with what's going on with this tetrahedral geometry. But we can look at additional geometries as well. So sp3 hybrid orbitals form these four sp3 hybrids that point in the tetrahedron. We can also think about a trigonal planar geometry. So these can't be the sp3 hybrid orbitals because that doesn't have the right geometry. And so this is formed from what we call sp2 hybrid orbitals. All right, and so these are going to form from only two out of the three p orbitals hybridizing. So we'll have one p orbital that doesn't hybridize. So if we represent it like this, right, we have our 2s and 2p orbitals on, I'm assuming we have a second row element here. And now we're going to take just two out of the three p orbitals and our s orbital, and they're going to combine. And so we'll have one p orbital that gets left alone, not part of the hybrid. And the other two combine with the s orbitals to form a set of three sp2 hybrid orbitals. That'll be a little bit lower in energy. Right, what do these hybrid orbitals look like? Well, they're going to follow this trigonal planar geometry. Right. So let's say, imagine we have a carbon. So we'll look at this molecule here, formaldehyde. Right, so we can think about what's happening with all of the orbitals here. Right, so this is a trigonal planar structure. We should get about 120 degrees, a little bit less than 120 degrees because we have a double bond here. But let's think about what these orbitals look like. So our 3 sp2 hybrid orbitals on our carbon atom are going to point at 120 degrees apart from each other and form this trigonal planar structure. All right. What about our hydrogen atoms? Well, they're just going to have their 1s orbitals, so those are going to overlap over here and over here, and so those form our 2 sigma bonds down here. Okay, so that's pretty straightforward. But what about what's happening with the oxygen in this double bond? Well, with the oxygen, we can look at its structure here. It's got 2 lone pairs and a double bond, and so it's also going to form sp2 hybrid orbitals. All right. I'm just going to erase this real quick. So it's also going to have orbitals that point like this. So our O is represented here, and we can write our carbon down here. And we can see these hybrid orbitals can also combine it. It's not just with s orbitals, but we have 2 sp2. So the sp2 hybrids are overlapping here, and that makes an additional sigma bond. And then up here we have our lone pairs. Down here we have our hydrogens. And we can see we have 3 different sigma bonds forming in this structure, right? So we have a sigma bond between the 2 hybrid orbitals overlapping, and then between the s orbitals from the hydrogens. Now, then the question becomes, what about the other p orbital? So on both the oxygen and the carbon, we have an extra p orbital that didn't become part of the hybrids. What's happening with that? And also, we've only formed 1 bond between the carbon and the oxygen, but if we go back to the Lewis structure, this is a double bond right here. So where's the second bond? So we haven't quite finished the story here. So I'm actually going to stop the video here, though, and we'll cover that and the idea of what's called a pi bond in the next video.